In this lesson, we're going to look at weighted graphs and networks. Graphs can include numerical information on each edge. These are physical quantities such as distances, time taken, and costs. These are called weights. Here is an example of a graph showing distances in kilometers between several towns. You can see each of the edges is associated with a distance. Sometimes you have to be careful to be sure what number relates to which edge. Clearly here between town A and town D, 8 relates to that distance, and the distance between town B and town E is 4. Networks are weighted graphs that represent real situations. Let's have a look at a problem from your textbook. Here is a model of the tracks in the forest connecting the suspension bridge B, the waterfall W, a very old tree T, and Fern Gully F from Sherbrooke Forest. Here we can see that walkers can enter the park either through gate 1 or gate 2. The numbers on the edges here represent the minutes taken to walk directly between these places. So we want to look at how long does it take to walk from the bridge directly to Fern Gully. We also want to see how long it takes to walk from the old tree to Fern Gully via the waterfall and the bridge. So the first part is easy. The edge that links B and F is here, and so that will take 12 minutes from reading off the graph. Now the path that links the old tree to Fern Gully, visiting the waterfall and the bridge on the way, is this path here, T to W to B to F. And we add up those times, 10 plus 9 plus 12 comes out to 31 minutes. An obvious question from the previous example is, what is the shortest route to take between two particular towns that are not directly connected? This is known as the shortest path problem, and it can be related to any type of quantities or weights in the network. In this course, the solution is determined by inspection. Here we first list the feasible routes and add the weights for each route. You don't list all the possible routes, as some are obviously longer than others. This method works well for small networks, but becomes increasingly difficult as the network grows in size and sophistication. You are required to learn some more sophisticated techniques in next year's course in further maths. However, I'm going to include one such technique in this series of lessons. Let's look at another example from your textbook. Find the shortest route between town C and town F in the previous network opposite. So here we have that one from our notes. Now first of all, we identify all the likely shortest routes from town C and town F, and we work out their lengths. So the first one, C, D, E, F, is 6 plus 9 plus 7, 22 kilometres. The next one, C, B, E, F, is 5 plus 4 plus 7 is 16 kilometres. And the next one, C, B, A, F, is 5 plus 7 plus 6 equals 18 kilometres. Now it doesn't make much sense to choose other routes via other points because they're obviously longer. Be careful though, sometimes you get fooled by the actual lengths on the diagram. The actual length of the edges doesn't necessarily represent the weight on the edges. So the shortest path in this problem was C, B, E, F, coming out to 16 kilometres. Just a note, you should compare the lengths of all likely paths because sometimes there can be more than one shortest path in a network and you may have to find all of them. You'll find your work in exercise 9A. If you need more help, continue this video and we'll have a look at question 3. In question 3, we have to find the shortest path from vertex B to vertex D in this network. The numbers on the edges represent costs in dollars. So first we want to list some feasible routes. In this first one, we're going to look at B to C to D. That distance is 7 plus 10 or $17. The next one, B to E to D, is 6 plus 5 or $11. The next one, B to A to D, is 2 plus 4 is $6. This happens to be the shortest path. Once again, it's important to realize that the length of the edges are not to scale, so focus on the numbers on those edges, the weights. Also, sometimes routes via 4 vertices are obviously longer, so they weren't one of the feasible ones. However, if we look at the first route we listed, which came out to $17, one of those other routes via an extra vertex actually comes out shorter at $13. You can check that out, B, A, E, D.